objectively, meaning what can we observe that everybody else in the room can agree on. Because when we get out into popular science, things out in the digital world, by chance, there's a lot of misinformation out there. We have to be careful. For instance, if I light this candle, we get what we would expect. Another combustion reaction, where you see light, and if you're close enough, there could be some smoke. There are things that you can see that everybody in the room can agree on. That is what an observation is, using one of our five senses to describe what we are sensing. When, in fact, though, we don't always reach the same conclusion. And we have to be very careful about what a conclusion entails. So if I blow out this candle, and we take a minute to process what we have witnessed, and then I say, but there's one more observation I want you to make. My afternoon snack is the candle. Now, you now can make a couple of interpretations.
Is he eating a candle?
This is coming through the microphone real. You really need to hear somebody chew. Joke's on you. I took too much of a bite there. The reality is, your interpretation, the human experience, is taking a situation and making predictions about what's going to happen. But our conclusions we have to be very careful about. I'm going to continue on without saying too much more about that, because I want you to think about it. If that were a candle, as we will explore later, would it have behaved the same way? And my thought is, I don't think so. I could be really nuts, which that's another conclusion that could be made. But let's talk a little bit more about candles and how they burn. See, the original chemical demonstration show came by way of a guy named Michael Faraday. Now, he is still very famous for 6 one-hour lectures / demo shows, all revolving around one topic, and that was the chemistry of the candle. How riveting, right? Think about that. That is looking at over 6 hours of discussing wax melting and burning. But it's a good sign of the times. Things change. Candles were big business. I mean, that's how you lit your home and the streets. I mean, my goodness, there probably wasn't anything in chemistry more important than the candle at that time. So it was a very important topic. Now, the next thing, I want you to pay attention to what I'm doing. I have taken cotton, 100% cotton cloth, and soaked them in a solution, which I keep introducing terms. Solution means a mixture of things in a liquid format. Now, what I want you to think about is, if they are flammable, that liquid, what would we expect to happen if I now set that liquid on fire? Well, let's do that, but let's do this in a way we make observations. Now, observations. That is the color. The heat. Do you feel it? Can you maybe even hear it? But the thing is, you have made also predictions about what should happen in this situation. And so if I shake this out and we put it back, what now can we observe? The cloth, it did not get consumed, much in the way a wick doesn't get consumed in a candle. The fact that the solution had 2 components. One was water. We have experience with water. It doesn't burn very well. It soaked the cloth and protected it. But there was another part of that solution in alcohol. Very flammable. And what happens is the alcohol goes to a vapor quicker than the water and burns. It burns just ever so slightly off the cloth and protects it, right? And so that's what happens. But notice there was some color there. Some color that's fun to demonstrate in another way. And that, we're going to tie together something here. I should put some gloves on for this one, because now my hands are going to smell great. Now, fork. All right, a pickle. I am going to take this pickle and impale it on some metal probes. I know, look away at the horror, the violence that I'm committing to this poor vegetable. Oh, all right. Now, if I pass some electricity through the pickle, I know that popping sound very well. And that was a fuse. And this isn't going to work. I wonder if it was this or if it was... I've done this demo enough to know when that has gone south. Bummer, dude. All right. Let me check one thing to see if it was, in fact,
say sour.
My extension cord.
That trick has gone
Or
sour.
not.
Pickle sour.
Nope, it was this. Okay. So all electrical items here are not going to work.
Oh, no.
That's okay. I'm a man who can think on my feet, because I'm not sitting down. So, electricity passes through its bumper, and there's smoke flying off of it, and it's glowing orange. And the point I've been making is to say it's the same color as one of the cloths, because they share a chemical substance in common, being sodium. When sodium is energized through heat, through electricity, it gives off a characteristic orange color. The other cloth was soaked in a lithium compound. It gives off a nice reddish color. It kind of almost teeters on purple. That has a lot to do with the fact that the alcohol has a bluish tint. So it's kind of a neat little play on the game there. But that is an interesting property of those chemicals, that if you energize them, they have electronic transitions that give us color, light. In fact, I think, if I were to guess, this room is full of probably halogen lights, that if you took a picture in here, the color is almost green because of the chemicals in it. Now, let me think about what would have been next. I'm doing great.
And then random.
I also usually do these shows with a partner, and I blame him, and now there's nobody to blame. So let's just keep on. And this is a fire demo. All right. And I said that wasn't working. Let me try one quick thing here just to verify.
Plug it into the wall.
Oh, I just blew that thing. That's good. That's good to know. Because the air, we're going to go back to the show. It's like I'm going to go right back in the character. The air is roughly 78% nitrogen, about 20-21% oxygen, to a lesser degree around 1% argon. Remember that. That 20% oxygen is very important to the air around us. In fact, it is one of the reasons why life on Earth exists. A lot of times in science we think, well, take a deep breath, and I say, well, what is that oxygen made of? What is that breath made of? And a lot of times people say oxygen because they're used to thinking about the oxygen that we use, but it's very important that we have the nitrogen to balance it. So, if ever you're in a room that catches fire, we always say, first and foremost, protect life and safety. Get out. Get everybody out. But you always hear that little addendum. Well, if you have a little extra time, which you usually don't, you want to close doors and windows. So here's the opposite of that effect. You think about a chimney, and we funnel in oxygen And we can get something really cool like that chimney. I tell you what, it could be Monday, but I guess it was Saturday. And if I put a barrier between the oxygen in the air, actually if I took the nitrogen, all the nitrogen and oxygen out of the air, what would I have left?
Argon.
See, you do this with a really intelligent crowd that kills the joke. You say that the air would be mostly argon. It's just plain out.
Yes.
I love it. See, a good scientist is like, I know the answer, but he's looking at me funny. Of course it's out. This is the exact same demo as my lady book. I do want to tell you, though, I did not blow the fuse. I destroyed my thingy. So we're good. Don't worry. No worries, people. I didn't ruin your stuff. See if I get invited back. Now, here, I want to kind of drive home the idea of the balance. Our atmosphere, you really have to appreciate that nitrogen-oxygen argon balance because it sustains life in ways we don't even really think about. You immediately come to terms with the fact that, yeah, we need oxygen to breathe. That's an obvious one. But another one we don't think of a lot is for combustion. We've utilized the combustion reaction, since the beginning of human time. And it comes in handy because that oxygen, we need that just right. So I am juggling some carbon dioxide. This is dry ice. You may have seen it, played with it. It's kind of a fun thing. If you think about the fact that we breathe in that oxygen, breathe out carbon dioxide. Now granted, we say that, but that percentage is really low. There's really not a lot of carbon dioxide coming out. There's really not a lot of oxygen reacting with the walls of your lungs. But the carbon dioxide is because we are carbon-based. In other words, the oxygen almost goes through a combustion reaction to give us carbon attached to it and it comes back out. We get enough of it, condense it, we can get this fun little solid that's really, really cold. In fact, I have to handle it like a hot potato because your hands, your skin reacts to extreme cold much the same way it does extreme heat. It burns, it blisters.
Cold potato.
But here is something that I think is super cool. Ask a chemist, say, man, are you a half glass or a glass half empty kind of guy or a glass half full? And I say, well, I don't get the question because I'm pretty sure the glass is always full. You say, what do you mean? Well, there's something in here. You just can't see it. Well, how do you know? I say, well, I know because here, if I show you, there's something in there that puts the fire out. I say, what? He says, no, really. The glass is full all the time. There's always something in there, whether you can see it or not. In fact, you can almost see where it's at because the flame goes down. I wish this was a little brighter. Well, see, it goes down when I get close to it. That's weird. So there's actually something a little more going on there. In fact, if I take a real candle, I promise you, this is a real candle. I don't know how, you guys are going to have trust issues with me now, but I promise you, there's really a candle there. And there's actually really something in this flask, or this beaker, that I can pour out onto the candle and make it go out. And if I talked through that a little too quick, watch that happen again. I said there was something in here. Now, granted, you see these little chunks of something here, but what's coming out of it? Is it a liquid? No, it's a gas. And gases
a gas
have
that's heavier
properties.
than air.
And so, if we want to say, okay, but what is really going on? If I pour a little water in here, we get a couple things happening. Carbon dioxide passes from a solid to a gas. It skips the liquid phase. So it's kind of an energetic process. And when it does, we put a little bit of water on it, we get that fun little fog that you get when stage shows or, when the mad scientist is doing his stuff, there's always some bubbling, and 9 times out of 10 they just put a little food coloring in it, and we're going to pretend we have some chemical reaction. In fact, this is mostly just all physical. Now, what this is allowing us to see is what's going on in here that you can't see. And now the water vapor is allowing us to pay attention to what's going on. Now, if I do this again, I'm going to light this little match, and now you can see it physically where that's at. It shouldn't be a surprise that once you get into the carbon dioxide, it goes out. It doesn't support combustion. There's a reduced concentration of oxygen there. And so now, when I pour it out, actually, there it's such harder when you can't see it, I think. But it does exactly what you expect here. Now, one other thing to point out is then what would happen if we had more oxygen in the air than we do now? So it's really obvious when it's less. So it's fire out. This is what we use in a lot of different types of fire extinguishers. But here we've got some bubbles. And those bubbles are oxygen rich. This is a chemical reaction taking place right now where the product is oxygen. So here we see if we put it close to here, it starts to go out. Yet if we put it over here, we get brighter. And I actually touched it too close. And so I just want to point that out. This isn't a horribly, I can't generate too much oxygen, so we have to do this in a subtle fashion. Oxygen is a little tricky to deal with. Right here,
Oxygen's flammable.
low concentration of oxygen, higher concentration. Lower, sometimes you get it to come back. Anyway, you get the point, right? So we live in a place where that oxygen concentration can't be too high and it can't be too low. Now, we have talked now about another concept, reactivity. Now, if we were to look at these balloons, we can make some observations. We would be very quick maybe to interpret or guess what's in them because of how they're behaving. They're floating. We can say they're less dense than the air, meaning there's not as many molecules packed together as there are. You know what? I just thought of something. I have to give you a little bit of a prequel to this. There's going to be a loud noise, possibly two. I need you to protect your ears when I do this. Now, a good way to do that is to give yourself elephant ears. Actually, if you do it right now, you're going to get an echo-like effect. Because sound travels through the air in waves, and if it hits your hand, it's got to go around. So it's going to diminish how quickly it gets there and protect it. So that is something to keep in mind. But I also want you to pay attention to something. They look an awful lot alike, but they behave considerably different. I'll just give you a hint. The first one's my favorite. All right, now observe, compare, and contrast to this one. Are you ready? Man, now that is what you call a letdown. So I color-coded them to know what's in them. So the two blue balloons are the same. The difference in the two over here had to do with reactivity. One was very chemically reactive. You saw heat and light given off. There was a little extra noise. We might even call it an explosion. Whereas the other balloon had a gas that all we heard was a release of pressure. That flame did nothing for it. So let's talk about then a different property of gases. And if we look at these, I like to tie them together because it shows us a big contrast. Actually, in fact, can I have two? You're right in front of me. You're just in my line of vision. So no favoritism. We come here for a minute. Now, this works to explain something that you're already seeing. Feel this balloon. Actually, feel it. Actually, hold it from the string if you want. But how would you describe that balloon? It's squishy. See, she's using some good terms here. How about, is it light, heavy? light. So if you let it go, where would it go? So you can go and let go. Yep. I think she's making some good observations. How about this one? What's that feel like? She says it's heavy. Anything else? Yeah, it's kind of hard to describe, right? It's green. Yeah, okay. Thank you. So she's confirmed something. I won't have any more volunteers at the moment, okay? So, but the other thing to point out then is, well, I would say, do you think they're roughly the same size? Roughly, we'll just say pretty close. Not a big size difference for you to think that one's way more full than the other one. There shouldn't be that big of a difference. The difference is how many molecules are packed in it. So this one doesn't have a lot of molecules packed into it. I wasn't carrying any proper equipment. And actually, I do need one other thing from over here. This has molecules that aren't packed as tightly as they are in the room. That's why it floats. Things less dense go to the top, things more dense go to the bottom, like the ocean of air that we're in. Now, if we think about that whole sound travels in waves thing, if we have our sound waves traveling through a gas that's lighter than air, it allows the frequency or the pitch to go up because they can wave or get there quicker. So what does that look like, sound like?
Well, first, it sounds like this. And what is happening, my voice has gone up, or we say the frequency has gone up. Because now my vocal cords can vibrate faster and it sounds different. So then I get the helium out, and my voice goes back to normal. We recognize everybody's voices, our friends, our family, because typically the density of the air doesn't change a whole lot on the surface of the earth. Now, if we go way up onto the mountaintops or way down below sea level, there is some variation, but it's not like you're hearing it. Now, I could be an actor, and so we always want to test things in multiple ways to verify something we've determined. I might be really good at throwing my voice, but this takes the guesswork out. Just an old organ pipe. You hear that frequency goes up. I can't fake that one, right? So, this balloon had a little bit of a difference in description. It's not just the same density as air, it's heavier. It's actually about 7 times the density of air. This is a pretty heavy balloon. The molecules are packed real tight. So, how would sound travel differently through here? Right? Let's think about it. Would the sound stay the same? No, maybe go down? Well, what would that be like? Now, as I begin this demonstration, I want to tell you, all the demonstrations I do up here, this one you can find very easily online, but I want to caution you, it's probably one of the more dangerous ones I do. So I don't want to take this lightly. This is fun, but there's an important thing I want to describe to you afterwards.
So if I breathe that gas, my voice goes down.
Sounds like a demon.
I'm really good at throwing my voice, but I promise you, I am a bad actor.
But here's the thing. That one is not, actually you can still hear it in my voice a little bit. So, the reason that this one isn't as safe to do is that density, the helium comes up and out real easily. The sulfur hexafluoride likes to sit in the bottom of your lungs and requires some effort. Here's the thing, I keep stressing that 20% oxygen in the air. As long as there's another gas in my lungs, I'm not getting the oxygen I need. In other words, I can only do this for as long as I can hold my breath. Okay? And it doesn't come out real easily. So these are all things that are very important. Now that's a lot of fun, trust me. I look forward. My wife says, stop it, don't do that one. I said, that is so much fun. And here, I'm just going to prove to you that it was not a trick. Again, the organ pipe. And you can hear that the pitch or the frequency of the sound waves has gone down.
Now it sounds like a bee.
Strangely satisfying. Okay.
Boing, boing.
Moving on. Oh boy, and we have, after the balloons, where how we get energy is really being explored. We can't continue on forever using hydrocarbons. You've all heard our fossil fuels are running out. What are we going to do about it? The byproducts, the greenhouse gases, all of these things are things we need to deal with. But I think it's very important that as we think about our future with hydrocarbons, we also look at our past, because hydrocarbons have done us a lot of good. We must thank those dinosaurs for all that they've done. And here's the thing. I have got to think this through. If I destroyed that, how will I make this work? I will keep moving, and I will figure this out. Hopefully it reaches. Now, the first thing to point out is, one, hydrocarbons have given us very energetic combustion. The heat and the light and the energy we have been able to utilize in a lot of different ways, mainly here recently, hydrocarbons in fossil fuels. The internal combustion engine. Let me just make sure this is going to work. Yes, okay, all right. The whole thing isn't completely lost. The idea here is that we do two different demos. One is to illustrate the energy of the internal combustion engine. One of the reasons we utilize it the way we do. So what you're witnessing is I've poured a fuel source into a cylinder. And I'm going to kind of overlap some terminology. In a car, there's a cylinder. And then there's usually some way to mix fuel and oxygen. Older cars, it would be a carburetor. Now fuel injection. And even now more advanced technologies. But the reality is, we only need vapor and oxygen for this to work. Excess liquid really doesn't do us much good. So I'm going to cork this thing because we need it to give off a good push. Now this could potentially be loud, so protect your ears. In fact, I'm going to protect mine for the first time, just to show you that yes, I am concerned about that. And I am going to supply a spark to our cylinder, much in the way we would a spark plug. So here it goes. Did you catch it?
I wanted to keep it.
Almost
You can't keep it. Stop it.
That's great. That's a lot of a good push of energy.
Pressure.
Everybody good? We good? I don't care about corks. Is everybody okay? Okay. Corks are a dime a dozen. Kids on. All right. But that energy push is very useful, but unfortunately there's something that was happening in this that is very undesirable that you couldn't see. So I'm going to leave this behind the blast shield, but notice I lost track of which one was which.
Uh-oh.
Always label your beakers when you get to school. I'm 99% sure I picked up the right one. This should be the waste from that reaction. It is. Oh, wait. So I'm supposed to do everything appropriately safe. Yes, that's good stuff. Okay. Now, I'm going to pour that waste liquid in here. And again, a friendly reminder, I am the human carburetor here, mixing our fuel and oxygen in the cylinder. Now, this is going to be visual. It's not going to be loud, but it's going to illustrate what happens or what we're looking at when we go to the gas station and we see that we have some options. There are numbers on the pumps, whether or not they are high octane or low octane. And so, without really saying much more about it, because this is a demonstration show, instead of getting too deep here, let's just look at it. So that was the initial push you saw, but watch what's happening in here. It's kind of a neat demo to watch, but it's not a real fun thing to deal with in an engine. Because what you get is a nice little push, and then all this knocking afterwards, all right? The low octane fuel. Engineering has come a long way in helping us use fuels like this. The reality is, we'd rather not if we didn't have to. Actually, one of the solutions to that was founded here fairly locally in Dayton with tetraethyl lead. And, well, unfortunately, lead in the environment didn't hold up very well. But if we consider then using a different fuel or a higher octane, and what that really describes is the degree in which there is branching in the molecule. Older students can understand what I'm talking about. Younger ones, don't worry, this one's visual too, right? Because that's the thing about being human and being able to think about things in abstract ways, right? The demonstration of a molecular concept, molecules we'll never see, but we can see how they behave through things like this. So, I want to make sure I get the dry one. I'm going to apply an activation energy to our cylinder, and pay attention to how this one burns. So apply a flame.
Wow.
And a nice smooth push. Well, there was a little bit afterburning, but notice how much smoother that was. That represents a higher octane fuel and more efficient burning. And while we're talking about materials, we want to try to keep this, obviously I'm the chemist, everything's chemistry, but really, notice all of the STEM sciences are involved in all of these demonstrations. This next one, I'll be honest, is, oh man, here we go again with this electricity. I think I can do it from over here. Let's see. Yes, okay. Something very simple. This is physics, this is material science, this is chemistry, all wrapped up in one. The first part to point out is as electricity in old light bulbs, they don't really work this way much anymore because this is a very energy-intensive process. As electricity passes through a filament, usually made of tungsten, it gives off light because there's heat and resistance. The other part is they're connected in series. Like those horrible Christmas bulbs. If one goes out, they all go out. See, if I break the circuit, they both go out. So the first thing I want to do is unplug it for safety. Take one of these out. Take a paper towel to cover it up. We're going to explore the light bulb a little more thoroughly. So I'm going to wrap it up in paper towel and then break it. Because again, breaking things, burning things, blowing them all up, they're all fun. Now, inside here, and I know this is hard to see in the back, but the reality, what we got here is two metal probes.